Good afternoon. Welcome back to Codex. Today, we're very happy to have Dr. Armenak Petrosyan. Armenak completed his PhD at Vanderbilt in 2017 under the direction of Akram Al-Drubi. Since then, he has held postdoctoral positions at the Oak Ridge National Lab with Dr. Clayton Webster, and now at Georgia Tech, working with Professor Chris Heil. Armenak's research is primarily in applied harmonic analysis, in particular dynamical sampling. But today he's going to tell us about some of his more recent research on machine learning and neural networks. Take it away, Armenak.
Thank you for the introduction, and thank you for the invitation to be able to talk in this very nice seminar. So yeah, my talk will be about integral neural networks with weight penalization. This work was conducted when I was started and at Oak Ridge National Lab when I was doing a postdoc, and I was working with initially I was working with Clayton Webster and Anton Birentsov, so part of the work will be with the collaboration with them, and then later on I worked with Konstantin Piper, and then we worked together and finished this project together. Currently I'm at Georgia Tech, but this is, like I said, the work mostly was done in collaboration with Oak Ridge people. So before I begin talking about my results, I'll talk about, just give an introduction on what kind of, what is our setting and what we are trying to do. So basically in general, the learning problem is we have some data, which is xi and yi, and finite data of size some k. And we are trying to fit a neural network into this data. So we have a neural network, which I'll define in a minute. It depends on some parameters theta. So theta is actually a vector. It has multiple components. So typically this problem is solved using backpropagation and with the loss function having this formula, which is 1 over 2 to the k, sum I equal 1 to k, and the network at the xi, the value of a network at xi minus yi, and plus alpha times r theta. So this first term is the fidelity. So we're trying to find a network whose response to the xi is very close to the yi. And then on top of that, we typically put some penalties on the weights theta. So alpha is some number bigger than or equal to 0 when it's 0. So we're not doing anything. We're just trying to fit the network. And or if alpha is bigger than 0 and we have this r theta regularizer, we're trying to impose some kind of regularizing term on the network nodes. So the issues that arise with this problem are there are many bad local minima. I want to emphasize this. So because we will discuss, you'll see that in our setting actually the local minima turn out to be nice. So, but in general, the local minima are bad. The issues are overfitting, lack of generalization, and another issue is the choice of architecture. So when you're designing your neural network, you don't know how to choose the specific architecture for the network. Okay, so our method is trying to address some of these questions in the setting that we'll describe in a second. So we have the neural network, which I promised to define, is a shallow neural network. So we're looking at the shallow case because this is easier to analyze mathematically, which is our goal. So we have a shallow neural network, which is a function of the form sum I equal 1 to n, cn, sigma an times inner product with x plus bn. So here the parameters are the a, b, and c. So an, the vectors, bn, and cn are the unknown parameters. So we're trying to find this or train a network with these parameters to actually fit our data. So the sigma function here is the Rayleigh activation function, which has the form the following form. It is 0 up to 0, and then it is the y equal x function for x bigger than 0. So pictorially, this looks something like this. So we can think of the x1. So we can think of the coordinates of x as x1, x2, xd as inputs, and each of them is being sent to this computational unit, sigma A1x plus B1. So the coordinates of A1 serve as weights on the edges from each of the xi to this computational unit where the sigma A1x plus B1 happens. And then sigma makes a decision in this node and says, okay, if it is negative, I'm not sending any output. If it's positive, it sends out the value itself. Then there is this weight C1 on the edge connecting to the output unit. And then in this output unit, the value gets outputted. So this is for the case when we have only single node. So in other words, in this summation, the big N is equal to 1 in the definition of the neural network, shallow neural network, that N is equal to 1. So I have just one unit. If we have many units, we can actually, like this, just as pictured here, we can stack them and then make the network a little bit wider. So the width will be the number of computational units in this network. And then each of them do their computation and then send it through the corresponding, send it to the corresponding weights, right? So C1's, these edges, and C1's modify the value, and Cn modifies the value from the nth unit. And then they go into this unit, which adds them up and then outputs the values. So this is the picture we want to keep in mind, and this will be the neural network that we're trying to train. Okay. So we can train in the neural network. We can actually, so initially I said we have some data xi, yi, but didn't specify where the yi comes from. But we're going to take a function approximation perspective. In this, we will assume that the yi is actually some response from some function fxi, for some function f on the xi plus epsilon I, where epsilon I are, for example, measurement errors, right? So we don't really have the true value, but we have with some small error. That's what the yi is. And then the goal is to train the network so that it approximates the function, right? So that's our goal. We want to find this function so that for the new input, when we get the new input for x, we can estimate the value of fx using the network. And so we basically, our goal becomes now we have our data, and then we're trying to approximate a target function using this data. There is this very interesting theorem, which was proved in late 1980s by, I believe, independently by these two authors, Sabenko and Funahashi. And it says that any continuous function can be uniformly approximated by a shallow neural network on any compact subset of RD with as much precision as we want. Okay, so basically for any epsilon, we can, in any compact set, we can find a neural network which approximates this function. But the issue here, the main issue here is that, of course, we may end up needing a really wide network. Wide in the sense that we'll need this number of these computational units may end up being really, really large if your function is not well behaved. And our goal in this talk is going to be to find a network as small as possible with as few or as narrow as possible, which approximates our target function. Okay, so that would be our goal, to find a network with as few as possible nodes or as narrow as possible, which approximates our function. I want to emphasize this. So to solve this problem, a method was proposed, and we will see that there are some issues with this method, right? So again, to remind you, the neural network has this form, sim Cn sigma an x plus bn. So our goal is to reduce the number of big N. So we want the big N to be small. And for the big N to be small, it is the same as saying we want the Cn's, the coefficients, the outer weights to be a big number of them to be 0, right? And so to solve this, Bengio and collaborators in 2016 proposed in a paper the following approach. So let's separate the weights into inner weights. So we write the theta as omega c with omega n being the inner weights, AN, BN, so the ones which are inside sigma. And then we have a CN, which is the outside, so outer weights. And so we'll think of this ANX plus BN as being selected from an infinite dictionary, right? So basically this dictionary is parameterized by the A and B. And so then this is the infinite dictionary from which we're trying to actually write a representation with approximation, with the representation. And then the suggestion was apply L1 penalty on the outer weights to sparsify the representation, okay? So again, our goal is to find a network which has few of these guys, of these computational units. And then the suggestion was to impose L1 norm on the C's, on the outer weights, and then hope that it will end up being a sparse network. It will be a network in which you have few representation coefficients different from 0. Yeah, and the spoiler is that the L1 penalty actually fails. Okay, so I'm going to actually explain to you why L1 penalty fails, and I'm going to suggest a remedy and show you that this remedy does better job than the L1 penalization. Okay, so first, before I talk about our suggested method, let's discuss why L1 penalty fails. Okay, so again, L1 penalty, again, our goal is to write a network which approximates our target function. And we want the big N to be a small number. We want to have few non-zero coefficients, right? One in representation. So the L1 penalized problem says, okay, let's look at the fidelity term, the one we always do, right? So the regression part, and then add the penalty. But penalty is on the outer weights. It's L1 norm of the C coefficients. And here, alpha is some number bigger than 0. And I want to point out here, so in general, we don't really impose condition on A and B, and there are any numbers. But the thing is, if you really want to have, due to the fact that the Rayleigh function in the neural network, it is positively homogeneous, you really want to impose this condition where you put A and BN to be on SD. If you don't put this condition due to positive homogeneity, you can take your network and then just one node split into multiple nodes on the same array. And then it's pretty much the same node, but you just artificially can inflate the number of nodes, right? So you have to impose this condition where A and BN are on the unit sphere in RD plus dimensional space. So kind of normalizing it. Again, without normalizing this, the problem wouldn't make sense. And then, yeah, we're trying to solve with the L1 minimization. And what is interesting, this was proved by the paper of Onji, Rayleigh, and others. Turns out this problem, even though it is a penalty on the outer weight only, turns out very interestingly, this problem is equivalent to penalizing all the weights, but now with the L2 norm, and then you have alpha over 2 coefficient in front, okay? So very interesting. So it seems like you're penalizing only the outer weight, but turns out that you're penalizing all the weights just by doing this, imposing this condition. So really, this is like the first sign that the L1 penalization is not gonna really work, because it's really under the hood, it's really just penalization of L2 norm of all the weights, okay? Yeah, and another really a bigger sign why really the L1 minimization is not going to favor sparse networks is because L1 norm is additive. So what L1 norm additivity of L1 norm really means is so this absolute value here in the CN, right? Absolute value of CN. This absolute value we can split into 2 CN. So we can write CN equals CN prime plus CN double prime. And if we do that, the thing is you don't really change the L1 norm. So L1 norm is not changed, again, because it's positively homogeneous. So you don't lose anything here. But on the right side, in the fidelity term, by splitting the node into 2 nodes, very closely positioned, you can potentially reduce your fidelity term. So when you train with L1 network, and I'll show you that when you train with L1 penalty, what happens is that you just end up getting a lot of nodes very closely positioned to each other. And that's the reason for that is the additivity of the absolute value. Okay, so this is, so really that's the bigger issue. The additivity of the L1 norm forces the network to produce many nodes very closely clustered to each other, and potentially reduces the functional, but really increases the number of nodes. So it does the opposite of what we expect. It instead of minimizing the number of nodes, it actually increases them. Okay. So to actually numerically demonstrate this happening, what we will do, we will look at this problem, which is slightly modified, and we also let the n, the number of nodes, to be a variable. So we allow the n to be variable also in the network. So we don't impose any conditions on how big the network. We allow the network to grow. So if it was a good network, if it was a good penalty, it would eventually have the solution would be some network which is reasonably bounded, right? Is finite or something like that, but turns out for the L1 minimization, this is actually you will see that this n keeps growing. If we try to solve the problem, it keeps growing. This problem now with this n bigger than equals 0 is actually a convex problem, and so if you try to solve this problem, you can solve it with very high precision up to any arbitrary tolerance. So you can set the tolerance and solve this problem, and then see what happens to the network. And what we did in this example, again, I'm trying to show you that the L1 penalization really fails to achieve what it promises in this case, right? Due to positive additivity. So in this case, we took we assume our data is sampled from -1, 1 uniformly, and we have 1,000 points. And we look at this function cosine 10 times 10 minus 3 plus x squared to the 1 to the 8th. And then yk is equal to fxk plus epsilon k with Gaussian, where epsilon k is Gaussian noise. And we look at the quadratic laws, just like we had before. So in this picture, we set alpha to be 0.01, and then we solve this problem up to certain precision, right? So and the fidelity term was 0.20 here. So we fixed the tolerance. We fixed some value of the tolerance. Then as soon as it becomes smaller than number, we stop there. Okay, so we keep running this with this value of alpha. So if alpha is small, alpha is this number, basically your fidelity term is going to be a little bit not great, but your network size is going to be somewhat small. And you can see here, even in this case already, there are these clustered nodes in the network. So they try to actually cluster right next to each other. And you will see this becomes even more dramatic as we keep increasing the number of, keep increasing the alpha. Sorry, keep decreasing the alpha. So, and then we try to make keep decreasing the alpha, and we try to, let me see, yeah, we keep decreasing the alpha. Alpha was in front of the, yeah. So if we keep increasing the alpha, we are forcing the fidelity term to be much better, right? So we're forcing a better fidelity term, and then network size keeps growing. So we are penalizing less on the network, and then as you can see, as we keep getting better fit, the number of nodes really just keeps increasing, and then they also increase in a bad way. They keep clustering next to each other, and then yeah, ultimately it just, for this value of alpha 0.001, 0.0001, we have 72 nodes, but they are very clustered. And then most of these nodes, like I said, they are artificially inflated. We could have these clustered nodes, we could have merged them together into one node and get a very similar approximation. But due to L1 minimization, it just favors splitting the network into smaller nodes. Okay, so hopefully I convinced you that L1 minimization doesn't work if you, or this convex neural network don't really work if your goal is to get a small network. As a remedy, we propose the following problem. So we propose that instead of looking at L1 norm, we take this function phi, which is non-decreasing. So basically everything stays the same. Simply instead of absolute value of Cn, we add this function phi. So phi now is non-decreasing, but sub-additive. Okay, so instead of being additive, it is sub-additive. So again, the problem with L1 norm was its additivity, because it was fine. It could have easily split the L1 norm into two pieces and be okay. The L1 norm wouldn't change. But now putting this penalty, this phi here, sub-additive, we are actually penalizing that, right? So we're saying if you split your node into two, then your functional is going to increase. So you're really not encouraged, or your training or your algorithm is not encouraged to, optimization algorithm is not encouraged to split the nodes, or it is more encouraged to actually merge them together. Okay, so and then therefore reduce the number of the network, not number of nodes in the network. Okay, so this is our proposal. Of course, we're going to put some other extra conditions on the phi, but this is the general idea. And then the spoiler is that this actually succeeds. So this works. We'll prove some theorems showing that in places where L1 norm fails, this actually works. Before I go to the next section of my talk, if anybody has any questions, I'll be happy to answer them. All right. So yeah, so this is going to be our problem, right? This is what we're going to solve, and I'm going to actually prove some things about it. So yeah, so basically my goal is going to, first of all, before I do any theoretical work, I want to show that the same thing we did for the L1, if we do with this guy, it actually this issue of merging this clustering nodes doesn't happen when we have the phi. So this will be just a numerical example. So for the phi, we took this function log 1 plus z over 2 plus z over 2. It satisfies the conditions, the technical conditions that I'll mention in a bit. And we take the nodes again, we take the sample again from uniformly on the -1, 1. We take the same function, the noisy data, and we try to solve this problem to the same tolerance. Okay, so we keep iterating that until the algorithm stops. And again, we take the alpha to be 0.01. And in this case, the number of nodes it finds already at the beginning is very small, n equal 5. And then the fidelity term is 0.14. And so if we keep decreasing the alpha, the number of nodes, of course, you get a better fidelity. Your network starts fitting the function better, and it has to sacrifice the number of nodes, right? It has to increase the number of nodes to achieve that. But the increase is very reasonable, and you don't see the similar type of clustering as we saw for the L1 minimization. Okay, and then again, due to this phi term being sub-additive, right? So makes sense in terms of the explanation I gave, I think, with that due to additivity and sub-additivity. But there are some issues with this problem. With the first thing that really should concern us is that the other problem was convex, right? Right away, seemed like a much better case in shallow. I'm talking about shallow case. If you go deep, it's going to be non-convex anyway. But in this case, with L1 penalty, it was a shallow problem. In this case, it becomes a sorry, it was a convex problem. In this case, it becomes a non-convex problem because it was sub-additive. And in fact, turns out finding the global minimum of this problem with high precision, the global minimum, is an NP-hard problem. Okay, so on top of all of these issues with convexity, that you cannot find the global minimum, it also adds the fact that you cannot find the global minimum with high precision. It's an NP-hard problem. So, okay, very bad, right? But turns out, actually, for this problem, all local solutions are good. Okay, so even though we cannot find the global solution, the local solutions are very good solutions. So no need to actually search for the global minimizer. So next section is going to be me convincing you that the local solutions of this problem are actually well behaved. And to do that, I'm going to introduce a much more general setting, and I'm going to prove things in a much more general setting, but they apply to this, to the whole thing, right? So it's just, I'm creating a theoretical framework for being able to prove that this is the local minimizers are good. So to do that, we'll introduce this integral neural networks. So again, I'm going to introduce a little bit more general framework to be able to prove the results. So we have some domain D in RD, and we have some omega set in RD compact, and M omega are the Borel measures on omega with bounded total variation. And then we have a sigma kernel, which is a Lipschitz continuous with respect to the variable omega, but the Lipschitz constant is bounded by the value of x. Okay, so if we fix the x, sigma omega 1x minus sigma omega 2x is less than the norm of that, the absolute value of that is less than equal to the norm of x times absolute norm of w1 minus w2. Okay, so omega 1 minus omega 2. Okay, so this is the condition that we will require, and then you will see that this is actually just a generalization of the setting that we had before. Sigma will be the Rayleigh activation function here simply, and omega will be the weights. And so we define the integral neural network to be the following quantity, which is this operator acts on the set of measures and its value is equal to integral of omega sigma omega x d mu omega. Okay, so this is a function of x, right? So it maps the totally bounded measures with total bounded total variation to actually continuous functions, right? Continuous functions on the domain D. And so let's convince ourselves that this is really generalizing what we had before. In our setting, the previous setting, omega would be simply the d+1 dimensional, the sphere in the dimensional sphere, which is in d+1 dimensions. And omega, sigma omega x was simply maximum of ax plus b or 0, and 0 for omega equal a and b in ST. And then if we took the Dirac measures, we took this finite measure, right? The finitely supported measure, sum n equal 1 and Cn delta omega n, then it will be bounded total variation measure. And on top of that, this network, when we compute this integral network with this measure, it ends up really being the standard network that we discussed before. So this integral network really generalizes the shallow network, and the way it does is you can think of this new network as an possibly infinitely wide network. Okay, so we allow the possibility of an infinitely wide network. And on top of that, you can see that the total variation norm of the measure of this measure here on the top is going to be exactly the L1 norm of the outer weights Cn. Okay, so this again the integral neural networks, and the problem that we'll consider here, the more general problem that we'll consider here, we'll assume we have probability measure mu, and we have a function L, the target function L, which is in L2 of D of mu, and then our data has the form yx equal fx plus epsilon x, and the generalized L1 penalty problem is going to be minimize the mu in mu omega 1/2 norm of the integral neural network minus the y, our data, L2 square plus alpha times the TV norm of the measure mu. And so this really generalizes the L1 penalty thing. But now in this case, we are allowing the data also to be infinite. So this even generalizes the case when we can have potentially infinite data, but finite data will be a particular case, right? So this really extends the L1 penalty to a more general setting. And the penalty term now is replaced with the TV norm. Okay, so this great. So this is actually generalizes the L1 penalization term to this setting. But how about the phi penalty, the one that our function that we're trying to minimize? Turns out you can extend the phi penalty in the same way. If you look at the atoms of this measure, nu, and you split into continuous part and the discrete part, then you can define this function of phi mu, which is the total variation of mu on the continuous part plus some n phi total variation at omega n summed over n, right? So this is, so on the atomic parts, you apply the phi and take the phi norm, and then on the continuous part, you simply take the regular total variation norm. And so the generalized phi penalty problem now will be minimized over all measures in m omega 1/2 norm mu n mu minus y, the L2 norm square plus alpha times this phi penalty. Again, if our probability measure was a discrete one, and if our integral neural network was with respect to discrete measure, this would become exactly the setting of the first few slides that we discussed, right? So the setting of the finite neural network with a finite data. But here we are potentially allowing an uncountable set of data, right? So this, we can think of this as like a big data problem. So you have large amounts of data and you're training your network. But again, the case when it is finite really still falls as a particular case of this setting. So after I introduce this problem, we will, instead of solving the finite case, we'll solve this more general network, integral network minimization problem, regularization problem. Some of the technical assumptions that we're going to make about the phi are mentioned here. So I didn't really specify yet what I'm requiring on phi apart from being subadditive, but we're actually imposing some extra conditions. We'll assume that phi at 0 is 0, its derivative at 0 is 1. So at around 0, it behaves like a y equal x, like the Rayleigh. And it's at infinity, it goes to infinity. We'll assume that phi is concave and non-decreasing. And then the derivative is Lipschitz continuous. So there exists a gamma bigger than equals 0, such that 0 is less than equal minus phi prime z2 minus phi prime z1 divided by z2 minus z1 less than equal than gamma for any z1 strictly less than z2. Okay, so the phi prime is Lipschitz continuous. So this is the minimum requirements that will impose on the phi. So in particular, L1 minimization actually still satisfies these conditions. But additionally, our stronger results will be proved if we assume that on top of this top inequality in the Lipschitz continuity of the derivative, another inequality holds. So gamma over 2 less than equal than minus phi prime z2 minus phi prime z1 divided by z2 minus z1. Okay, so but this thing we only want to be satisfied around 0. We don't want it to be satisfied for all values of z. So as long as this is satisfied around 0, we're fine. So this is kind of a strong concavity condition, and the graph of the function looks something like this. So the yellow curve here is the Rayleigh y equal x, and then the blue one is the type of phi that we want, right? So we want it to be a little bit curved. So we want it to be concave, but around 0 behave pretty much y equal x. So some of the functions that satisfy this conditions would be this phi function, or if you take I think actually phi will not satisfy maybe the limit goes to infinity condition. So we want to actually, no, it satisfies, I'm sorry, it does satisfy, yeah. So this will satisfy 2 log 1 plus 2 gamma z divided by 2 gamma. This satisfies all the conditions. If you take any two phi which satisfy these conditions and you take their convex combination, it still satisfies. So phi z and so this combination of this guy with the L1 norm still satisfies. Or there is this MCP functional, which is discussed quite a bit in statistical literature for non-convex penalties. So kind of non-convex lasso, they also satisfies this condition. Okay, so this, yeah, so our setting really is MCP also falls into our setting. Okay, so these are the technical assumptions. This is the setting. And so our target functional that we're trying to minimize is going to have this formula, right? So this is the function we want to minimize. Is 1 over 2, and the network gets measure mu minus y, the data, L2 norm plus alpha times phi of mu. So let's define what we mean by local minimum of this functional. So a local minimum, measure mu is called, mu bar is called a local minimum of this functional if there exists a delta bigger than 0 such that the j at mu bar is less than equal than mu bar for any, mu bar is less than equal to j mu for every mu which is in TV norm at most delta distance away from the mu bar. Okay, so this is the local minimizer in the strong topology. So there is the first result that we proved was that if phi satisfies conditions of phi1, phi2, and phi3, then all local infimum values of the g mu are attainable, right? So any if you look at the local neighborhood, you look at infimum, then there exists a value which attains it, right? So it's we can give actually a little bit more technical definition of this local infimum, but basically, if you're trying to approximate an infimum value inside some neighborhood, you're going to attain it. You're going to eventually converge to it. So this is the first result, that the local minimizers are local infimum values are attainable. Then the next really to me. I think the more interesting result is that if phi satisfies the conditions phi1, phi2, phi3, and phi4, and x and yx are in L2 of d mu, and mu bar is a local minimum of the j. So remember that we are potentially fitting an infinitely large data set. So we didn't put any conditions. So if you have large data set, you're trying to approximate it, you will, if your function is not good enough, basically you will need to keep increasing the size of your network, right? You'll be forced to increase the size of the network to get a good approximation. But what this theorem says, it says that if you solve the problem, any local minimum is going to be a finitely supported measure. So in other words, it is like the standard neural network that we started with. So if you try to minimize this general problem, try to solve the general problem, its solutions, all local solutions, are going to be finitely supported measures. Okay, so the solution you're going to find is going to be a finite network. This doesn't happen when you look at the L1 minimization problem. Okay, and on top of that, there is this strong representer theorem, which says that if you start with a finite data, then the size of your network is not going to exceed, for any local minimum, is not going to exceed the size of the data. Okay, so this is a strong representer theorem because first of all, it holds for any local minimum, and the representer theorem for L1 minimization, it says if you have a network, local minimization, local solution of the L1 minimization, finite network, you fix the number of the width of the network, you solve it, you can rewrite this network in a way that it has at most n nodes. Okay, so it doesn't even, in L1 case, it doesn't even really say that any global solution has nodes less than equal n. But this one says any local solution, you don't have to rewrite it, any local solution has this representer theorem holding for that the number of nodes is not going to exceed the data. Okay, and then of course you might be saying, okay, so it's good, you're penalizing the weights, you find a sparse network, right? But what if you're penalizing too much? what if you're sacrificing the size of your network for the fidelity? You can find out, okay, take a network with one node, but it has a really horrible fit to your function, right? The next theorem shows, on top of everything, that that you also, with local solutions, you get the good accuracy. And to estimate the accuracy, we're going to introduce the following quantity, which is this f star norm, which is, so we look at the functions. So we look at the function f and try to write the f explicitly, so exactly equal to a neural network, new almost everywhere in D. And among all possible, so this may have multiple solutions, so it may have a kernel. And in the kernel, among solutions, we look at the one which has the smallest TV norm. Okay, so in the next slides, I'm going to actually compute this f star explicitly, and then I will, for a function, you will see what this is equal to. But for now, just take it as some quantity associated with f. So the next theorem says, if the phi satisfies condition 1, 2, and 3, and nu bar is a local minimizer of the functional local, then the fidelity term from the local solution to the true function is bounded by alpha times the f star norm plus epsilon, L2 norm of the epsilon. Epsilon was the additive noise, okay? So we really want to concentrate on the first term, assuming that epsilon is small, the noise is small, its L2 norm is small. We really want to concentrate on the first term. And so alpha typically is chosen to be a small number, right? So basically, it is bounded by the small number times norm of f. And then, so basically, then now the approximation comes down to how big this f star norm is. And then I will explicitly compute this f star, and you can see for what functions it's going to be large. So yeah, so these are the three basically nice properties of the local minimizer. So you don't really need to, you can solve the problem. You don't need to look for the global solution, because finding global solution is an NPR problem, even if you're doing it with high precision. But the fun thing is that all local minimizers are actually good. So and like I showed you, they have this finiteness property, which you cannot hope for the L1 minimization. They have the strong representative theorem, and then they have pretty good accuracy in approximation. Okay. Other questions from here before I proceed? All right. So like I promised, in next section, I'm going to actually compute this f star norm. Let me do that. I'll go over it a little bit quickly, and then I'll talk to you about the algorithm that we use to approximate it. So this representative norm basically the picture doesn't look very nice. So we are limiting ourselves to the case when we have our Rayleigh functional. Omega is the SD, sigma is the Rayleigh, D is the whole RD, and the support of mu, the probability measure, is equal to RD. And we denote by mu D the Lebesgue measure on SD. The RF is the Radon transform, and then H is the Hilbert transform. And then the following theorem holds: if F is in a CD plus 1 space on RD and is compactly supported, then for any, so I'm sorry, I forgot to mention this theorem in its stronger version was proved by Onji and collaborators in 2019. We posted our paper pretty much concurrently, but our result was much weaker. Okay, so we only showed that F can be represented in this form, but we didn't prove that this is like this if and only if condition. The stronger condition was proved by these authors, but the paper was posted pretty much concurrently. And so the theorem says if F has this compactly supported nice function, then F can be written in the form of n mu x if and only if mu is a measure of the form mu f plus mu odd. Mu odd is any measure which is basically odd on the unit sphere in D+1 dimensional in the D-dimensional space. So it is when you flip it, it changes the sign, and the new f is given by the following formulas, which I'm not going to go into details over for the sake of time. But this, if you take a Fourier transform of this guy, it actually looks a little bit better. It is some kind of a kernel which modifies the Fourier transform. And for the odd case, nu f has one formula without the Hilbert transform. In the even case, it has the Hilbert transform. And you should probably guess from here that in the Fourier domain there is absolute value or norm involved there, right? So that's why there is this Hilbert transform. So why is this theorem actually nice? So it solves all possible representations of a function in the form of neural network. Turns out the star norm that we discussed was exactly the TV norm of f, or this TV norm of this measure on SD. Okay, so this really really gives you the exact formula. So if you want this f star to be small, you somehow want to have this guy to be small, and that to be small it has to do with the smoothness and stuff, right? So we haven't really analyzed this formula that much. I don't think anyone has done. I don't think the other authors have also analyzed this formula, but this is what you get. The f star norm is given by this formula. Okay. I'm going to go over a little bit quicker for the rest of the section, and then basically we again showing you the case of the when d is equal 1, we have a one-dimensional function, so that nu f can be explicitly computed. So this formula is actually very easy to compute when d is one-dimensional case. In one-dimensional case, the network can be written as integral sigma cosine phi x plus sine phi d mu phi. And in this case, now the mu phi has very explicit formula. And then in this picture here, we actually try to solve the L1 minimization problem with high tolerance, and then with small tolerance, and then we keep adding nodes and so on. And then you can see that actually it starts resembling what we expect, the solution of this L1 problem in the with this new f, right? So these guys really start resembling the continuous function, and so this is another really a proof that if your function is good enough, your L1 minimization problem is really going to approximate a smooth function and going to fill in the smooth function, and then you're not going to get a shallow network. Okay, I'm going to skip over this result, and then I think I'm going over time. Is it okay if I go over like 1 or 2 minutes, a little bit, just to discuss the algorithm?
Yes.
Yeah. Right. Okay. Just very quickly, just to basically tell you how we actually solve because I told you that the n is a variable there, right? So we need basically every time we need to add somehow modify the size of the network, and that's done with this generalized conjugate gradient algorithm. So we initialize the network, doesn't matter how we initialize it. And so we do the greedy selection. We find the node which is the most correlated with the residual of the network, and then add it to the network. Then we apply we find the corresponding coefficient c using a proximal operator, and then we update the weights by solving this optimization problem, which is now n is fixed here, and then in the extraction step, we remove the nodes which are 0, and we keep iterating this. Okay, so basically on every step we are adding a node and removing some nodes, adding a node, removing some nodes. So this is modifying the network on every step. It can, in some cases, actually you may start with a network, you can decrease the size, and you increase the size, you decrease the size. So really the size keeps changing. And so this can be extended also. Instead of inserting one node every time, you can actually insert more than one nodes on every iteration. This is basically the algorithm we use to solve the problem. And here are some numerical examples. Basically, here we show that the gamma here, the quantity gamma here, is the how different your so if gamma is very small, this is the tangent of the quantity that controls how concave your function is. If gamma is very small, you're very close to the L1 norm, and then in that case we saw that we get like a really large number of nodes, and then as we keep increasing the gamma, the number of nodes, so phi becomes more and more concave. You find sparser and sparser network without sacrificing your fidelity. Okay, so this really shows that by increasing the gamma or making it more concave, you're not really sacrificing the fidelity term, but you get improvement in the number of nodes. And then we had a two-dimensional example. To be honest, the two-dimensional example is not as impressive as the one-dimensional case. The multi-dimensional case really needs more work. So at the moment, this is more a theoretical result. Multidimensional case, the sparsity is not as impressive as in the finite dimensional case. So maybe imposing some extra conditions on the phi would actually make it better. So maybe the conditions we have are not really the final ones. We need to put some more conditions on phi. And so the work, the paper which I presented from are the non-convex penalization for sparse neural networks with Constantine, and then the parts with the integral representation where we compute this F star norm. It is in this paper with Anton and Clayton, and then also in the Onji Roulette paper, and another paper on this convex neural networks, which is highly cited, is the paper by Bach on the breaking the curse of dimensionality with convex neural networks. Okay, so thank you very much. Thank you for your patience. Sorry for going over time. Did I go over time, or I still have a minute? I don't know. Doesn't matter. I'm done. Thank you very much.
Thank you so much. All right, everybody, smash that reaction button. And Dustin can hit the end recording button.